Okay, so there's a pile of other considerations that need to be considered when you're going to weld something. It's not just a matter of picking up one of the various tools and striking an arc. One of the first things to think about is what is it you're welding? And particularly with ordinary carbon steel, there is a very well-defined set of numbers that tell you what is in the actual steel. It's a 4-digit code is the one normally used in Australia. There is also a British standard, which gets used as well, where we talk about EN26, which is sort of the same as 4340, but slightly different. But the easiest one to think about is the SAE or ASTM standard, which the 4 digits, the last two are the percentage of carbon in 100ths. So a 1040 is 0.4% carbon. And the 10 tells me that it's a plain carbon steel. I mentioned just a second ago 4140 or 4340. Those are these guys here, which are a molybdenum steel. If you're talking about springs, you're often talking about a 5160 type of steel. So knowing or having some idea what it is you're trying to weld will also help you understand what its weldability is like. And a lot of this comes down to what's called the carbon equivalent. And so if I'm looking at just a plain carbon steel, take a 1030 for example, I can pretty much weld straight onto that as long as I cool it nice and slow once I've finished. Don't put it in front of a fan or, heaven forbid, quench it. But if I'm looking at this guy here, the 4140 or 4340, that 4 and the second number add effectively to the carbon equivalent. So anything up to 0.4% is deemed as readily weldable. Beyond that, you've got to do specialised processes of preheat and post-heat and other such things. So you just need to be mindful that there are these other things out there in the world. The heat treatment also impacts on your weldability. So if I get a fully annealed piece of 4140, I can probably comfortably run a bead of weld along that. If it's got a volume of thickness to it, I might want to preheat it a little bit to stop the quench at the weld pool. But that'll weld and it'll be okay. However, if that 4140 has been heat treated, then I am asking for it to fail if I weld on it without doing a lot of preparation, both pre and post. So again, just keep in mind that, welding is fairly straightforward, but there's a lot of fine detail and complexity in it. So that was just touching on carbon steel, mild steel. There is also stainless steel and aluminium. There's a Wikipedia's got everything these days, but Wikipedia's got a bit of a pile of information there. If we look at stainless steel, we can get austenitic, martensitic, ferritic, and duplex, and I think there's one other grade as well. If we look at austenitic, 304 and 316, surgical stainless is basically 316, or an 188 alloy, 18% chromium, 8% nickel. And the tip is if you walk around with a magnet, austenitic stainless steels are not magnetic. That's sort of how you tell them apart. Anything with a 3 is going to be an austenitic stainless steel. When you go to a martensitic or a ferritic, it's a 4 something something. And from what I can see, I'm not great with stainless. Some of the 4s are an are a martensitic, and some of the 4s are a ferritic. The other thing just to keep in mind, it's stain-less, not stain-proof. So I've seen an article talking about the Tesla Cybertruck, and recipients are reading the owner's manual going, OMG, I can't wash it, I've got to do all these things because it's going to rust. And it's stain-less. And certainly if you look at a lot of the ferritic and martensitic stainlesses, they oxidise, and they rarely look like a polished piece of 316. Okay, if you're going to weld stainless, you'll probably use a stainless filler rod. And again, you just need to be mindful that it's the right filler rod, it's the right processes. They have different properties. Aluminium, just as complicated, if not more. There's age hardening, there's not age hardening or not heat treatable. If you're going into your kitchen and you open a bit of aluminium foil, it's going to be an 1100 grade, which has a yield strength of about 60 MPa or something silly like that. 2021, 2024 are commonly round bars. These guys tend to be in sheet form, although this can also be done as a round bar. 7075 is so-called aerospace grade. But all of these will have different ways in which you can weld them. One of the difficulties with welding aluminium is the oxide layer melts at a higher temperature than the substrate. So it can be challenging to weld, and that's why TIG is predominantly the thing to use with aluminium. You run an AC alternating current through the tip. Half the current pulls the oxide layer off. The other half of the cycle deposits metal down, if you like. It's worth just looking up some of the stuff if you're ever involved in it. As I said, carbon equivalent and temper are both important considerations. In general, unless you're going to do some sort of a post-weld process, you're going to assume that you're going to end up at a hot rolled state. So if I get a bit of C450 RHS and I weld it, then all of a sudden I'm down to a 350. This is an MPa yield stress. So I've already lost quite a bit of strength in and around that weld. So hence I want to try and get my welds out of the highest stress zones if I can. Because we revert back to a hot rolled state, it's why we tend to rivet aircraft and race car monocoques. Because if I've bought some U-Butte 7075 alloy sheet, and I might have a sigma yield of 400 MPa, as soon as I weld that, I'm back to about 80 or 70 MPa. So I've lost an enormous amount of strength. Hence, we want to rivet it wherever we can in that sort of situation. A little bit of weld nomenclature. We've got the root of the weld right down here in the corner. This is sort of the throat, the usable thickness of the weld if you're doing stress calculations. Toe of the weld, where the weld joins onto the parent metal. You've got, a fusion zone here. Hopefully that's a nice solid amount of fusion. Extra reinforcement here, which is the same as up on there, which does nothing. And in fact, particularly with fatigue, you want to grind that off and polish that up to at least the condition of the surface. So this is obviously a fillet weld, this is a butt weld, same terminology. You will quite often get, if you're doing thick plates, there is a limit to how much weld you can put down in a single pass. So you might end up doing one weld here, right, and it's got a fusion zone or a heat affected zone out there where you're melting this pool of metal, gets melted into it, right, and then you've got to come back over that and put your second or third or fourth run to get the required thickness. And of course, whilst you're doing that, you can see here in this image, you've got a heat affected zone through here. You've got a fairly fine microstructure in the as rolled plates. And in the weld, you can see we've got some fairly large crystals or grains. So that's cooled relatively slowly. So it's fairly obvious that through here, there is going to be a variation of mechanical properties. So you just got to be mindful of that. There are a lot of possible or common defects. This depends, if you've got a really good welder, trade qualified and very experienced, they will lay beautiful bee to weld down every time without even thinking about it. If you or I pick up a welder, we're likely to do every single one of these errors. Porosity is a often thing. If you're using a MIG welder and you forget to turn your gas on, you'll start welding and you'll get a real bubbly weld pool where it runs out of gas, which you've then got to go back and grind out and weld back over. Undercut is, again, a defect, and it causes a problem, again, with stresses because you've reduced the thickness. There's a lower thickness through where that undercut is. And that undercut can either be in the weld, but it can also be in the area adjacent to the weld. And so you might have the weld metal built up enough, but you've undercut the parent. And therefore, again, you've got a lesser thickness to deal with the stress, as well as, a stress concentration because of the shape of the thing, etc. Underfilled, well, okay, I can come back and put an extra couple of beads on there. I need to be mindful of interpass temperatures, and, if it's a stainless steel, I might need to be worried about keeping it above a critical temperature for too long. Poor pen, lack of fusion, that's again, a good welder will not do those errors. Spatter, any MIG or stick type process, you're going to get some spatter, and you'll normally spray the job with a spatter guard to enable those little bits of rogue metal not to stick. But again, you've got imperfections sitting on a surface that might cause some stress concentrations. Overlap, stress concentration. To get this, this is probably going to be a fairly cold joint there, perhaps. So it may cause all sorts of other problems. Inclusions, if you pick up a stick welder, anyone fairly new to stick welding will end up with inclusions galore in their welds. And of course, that's just a place for stress concentrations to start. Excess reinforcements, self-explanatory. Cracks. So if I use the wrong filler material or I use the process wrong, I might get cracks here in the heat affected zone, or I might get cracks in the weld pool itself. And so that's obviously going to cause early breakage under loads. And so again, understanding the process and what it is you're welding and what you're trying to achieve is sort of the first step in understanding this sort of stuff. I mentioned multiple run welds, and these two images are a great example. So we've got a fairly thick plate here. You're not going to weld that in one pass. Now here they've got what's called a root run down, so somebody's run along and put the first bead of weld, and you can see the heat bloom on that side at least where it's blown through or blown the heat into the job. The next image across, you can see these plates that are tacked on to the edge. They're fairly little thin plates tacked onto this big fat heavy plate, and you can see all of the beads of weld. Now I've got no idea how thick this plate is. These beads of weld would have been done with what's called a submerged arc, which I didn't mention. But if you imagine a really, really, really big MIG welder with a continuous wire feed, but the wire is, perhaps 3 to 4 millimeters in diameter. But unlike a MIG where you're using a gas as a shield, you use a granular flux. So it only works in a downhand position. You pour the flux on the job, you automatically index it's on a little robot that runs along the weld, feeding the wire in the right rate. You can see the completed weld underneath the slag. Basically, you vacuum up any unused slag, protecting, I forget the name of the damn stuff, the flux. You vacuum up the unused flux, and you chip off the slag ready. And you can see here we've got a wire wheel, so somebody has to go along there and remove any slag that's left from the flux before the next weld is set up. The reason why we have these plates is to do with this heat coming out of the side of the plate here. If I simply start welding here and start going in and it's cold, the first little bit of this weld is going to be cold. I'm not going to get full good penetration. And it's much the same at the other end. I probably want to have a runoff plate. You can't see it here, but I would imagine there is a runoff plate at the other end. And once we've finished all these dozens and dozens of welds, we cut this bit off. And so we've got good quality weld all the way through the job. The other thing I've just shown here is a motorbike frame, just as an example where you'll see a whole heap of different welds. So each one of these is probably done with a robotic TIG. You've done a lot of tube profiling to get these to be exactly the right shape so that you can use the minimal amount of filler as that gets all welded together. Some basics of welding symbols is useful or important because you guys will be sticking them on drawings. If I've got a T-joint like this, I can point, and this is my welding symbol, and the way you read this is I want a 6mm fillet weld on this side of the joint. If I'm talking about the other side of the joint, so the one that the arrow is not pointing to, I might have something different. I'll do the same in this case. I'll put a 6mm fillet weld on the other side of the joint. If all I had with that, then the job would come back with this weld on it, and this one would be empty. So it's important you understand what it is you're specifying when you're doing your drawings. You might put other information. You might specify that it's with a MIG. You might tell that it's a stitch weld. Weld 50, skip 100. And so in that case, you will end up with a weld that will have a 50mm weld, a 100mm gap, and a 50mm weld for the length of the however long that is. And of course, you can build these up in all sorts of weird and wonderful ways. If I'm going to do some sort of a butt weld, so let's finish rubbing that off. I might have a symbol that looks like this. I want a butt weld on this side. It might be 3mm, whatever. And I might want to leave it with, it looks like a smiley, a convex finish. So what I would get at the end of that would be hopefully a decent amount of penetration and a weld that had a positive contour on the outside of it. All right. The other things you might come across, if I put a circle around that, means weld all around. If I put a flag on that, that means it's a site weld, which probably means your cost has just gone up a factor of 3 or 4 because they've now got to do it on site without all the stuff they've got in their workshops. If you're joining pieces of plate together, for example, or anything, it goes across all sorts of things in engineering, you don't want to have a step change in the stiffness of the object. Stiff points will attract load and therefore fatigue failure. So if we've got a thick piece of plate and we're joining to a thinner piece of plate, either like this where we've ground it down or chamfered the edge of that plate so that there's a bit of a progression in that stress. It might be that you need to do like this if you want those two plates to line up on that side. But in all cases, you want to try and transition that stress or strain more progressively than if you do this, that's where it's going to fail, pretty much. So keep in mind when you're welding, you're putting molten metal onto a piece of other metal. So as it cools, it'll go from its liquidus to its solidus at, I don't know, 700 degrees. I don't know what it is for steel, might be a bit higher than that. But from there on, it's basically solid, and all of that contraction as it cools back to room temperature is going to want to pull the metal you've put it on. So if I look at a butt weld, I've got more thickness up the top than I do at the bottom, so it's going to pull inwards. And so your two pieces of plate will end up not sitting flat if you've welded them when they were flat to start with. There's also a time factor here. Because I might start at this end and weld through to that end, different things have cooled at different times, so we might get a bit of a warpage this way as well. So one way we can try and limit that is stitch welding, but also to put a weld here and a weld here and then a weld there, and these are things your welders are really the experts in. Talk to your welding professionals, because they'll be able to give you an awful lot of help in this stuff. Same sort of thing with a fillet weld. If I weld a T section up like this piece on this face of the metal is probably yielded. I've probably pulled that so tight that I've yielded that face. So if I want to make a weldment like this and end up with it being flat and square and true and all those sorts of words, it's not particularly a trivial task. You've really got to plan it and think about it. You might need to stress relieve it after it's welded by heating it up and soaking it at temperature. So again, just things to be mindful of. A little bit of secondary consideration. If you're doing non-symmetric welds, which really you shouldn't, if we look at this guy here, if I pull that, it's going to create some sort of a moment about that weld, and it's going to try and rip it out from the toe. Right? You put a big moment there, it's going to want to destroy it. The way to fix that is obviously just put two welds on it. Now if I pull, there is no moment. All right, so I've symmetricized the loading schedule. Same deal here. If I've got two pieces of plate like that, this one's going to want to roll that way, that one's going to want to roll that way. You put all sorts of ugly stresses into those welds. Put a fillet on each side, it just becomes a pure shear through those two fillets, easy to work out, robust. So a true stress analysis is pretty complicated. You've got a lot of things going on there. Moments through the heat affected zone, you've got all sorts of different material properties from the parent material through the heat affected zone into the weld metal. It's very ugly, if you like. So how do we do it? Well, we simplify everything. Simplification, everything fails in shear. So any weld we're looking at, we are going to assume it's going to fail through there, basically. I will point you to a number of Australian standards. There are others, and I think there's even others in this presentation. So first and foremost, whenever you're doing any sort of mechanical design, you should be looking up what standards apply. Okay, so if we look at a butt weld in tension, the stress created from this load P is H over L. Now I'm using H over L here, H over L, because this is what conventional theory says. Right? This probably over-exaggerates the stress in the weld, but that's far better than underestimating it and having it fail. Butt weld in shear, again, H on HL is your active area. The shear stress, that makes pretty clear sense that it's going to be a shear. Fillet welds, we're going to work that the shear stress 0.707 HL gives me this thickness through here, the 0.707. Right. So that's why the shear stress is 1.414 P on HL. So that's all fairly straightforward. Just something a little to the side, you might often see a tag welded onto something for whatever reason. There is a limiting value of B over L. Well, I guess it's not limiting, it just becomes pointless. If B over L is 1, all right, so I've got a 50mm wide plate embedded by 50mm, then I can utilise about 70% of the capacity, I guess, of that tag. If I've got a 200mm wide plate that's only embedded 50mm, then I'm probably down here around 35% or 25%, whatever that line should be looking like. Yeah, more like maybe 30%. Because the stress can't propagate from the weld way out here sensibly and support the middle, okay? So you just need to be mindful of that. Similar but different if you had a really, really long overlap. You're not going to fully activate all of that weld because you just can't. It just doesn't work that way. So if we look at a fillet weld loaded parallel to its length, stresses calculated throat. This is the image a couple back. So I hope that's fairly clear that, again, we've got the H 0.707 H to get the width through the weld, and then times L. So we end up, again, 1/0.707 is 1.41. So that's pretty straightforward. If we're looking for a factor of safety in static loading, the shear stress at the yield point is about 0.577. And this comes from distortion energy theory, which I think is a couple of slides ahead. So you can work out what your shear strength is, what your allowable shear strength is, get a factor of safety. Okay. So distortion energy theory says that it'll yield where the strain energy performance per unit volume exceeds you can read that ugly sentence. What it means really, we've got two different graphs here. The maximum shear stress theory is this guy. And this is somewhere in chapter 5 of Shigley. And basically, if we've got a plain strain piece of plate, if sigma 1 and sigma 2, I'll call it sigma A and sigma B, if they are both in tension, then you'll fail somewhere along this line. If they're both in compression, you'll fail somewhere along this line. And if you've got one compression, one tension, the failure will be along this line. That's what the maximum shear stress theory says. Von Miser and others came up with this, and square corners aren't really good in anything in engineering, so it doesn't make a lot of sense for it to be a square corner. So there's lots of data for a ductile material that gave this sort of a profile, and this parameter ends up where you're somewhere here, which is 0.577, compared to 0.5 for the maximum shear stress theory. So you could use tau equals 0.5 sigma yield, and it'll just be more conservative. So it depends how critical you are aiming for a fully optimized solution, I guess. Okay, so if we look at permissible stresses by one of the welding codes, and again, AISC is an American code, it's saying that if I've got tension in a butt joint, I can only use 60% of the yield strength. Bearing, which is the same as compression, in a butt weld I can use 90%, so it's a much more greater capacity. Bending, simple compression, shear, etc. And I believe that these are basically, if I use a qualified welder and I follow decent weld procedures, I am covered as a professional engineer in using these stress levels. It doesn't mean you can't go higher, but you would want to do specialist inspection, radiography, NDT, ultrasound, to make sure that the weld was perfect. If you're building the space shuttle, I would imagine you are running much higher permissible stresses because weight really kills when you're trying to lift off from Earth. If we start to look at the stresses in welded joints, you've got three basic types: primary shear, secondary shear or torsion, and bending. So if we look at primary shear, if I've got a plate welded onto a bigger plate, all right, then I can work out what the area of those welds are. All right, cross-sectional area. I've got a force. My primary shear is simply going to be P over AX, where AX is that. So stress equals. Right, so that's very simple.